Hi, this is Elias Fofanov, aka Engineer Spock from engineerspock.com. This section is the introductory one. In this section, you'll learn: what is a unit test? What unit test frameworks exist? How to write a unit test in practice? Naming conventions. How to run and debug unit tests. What are the benefits of writing unit tests? Who should write unit tests and when? The oath of a programmer and how it is related to unit testing. Let's get to the section and start with learning the basics of unit testing. In the next lecture, you'll learn what a unit test is. The problem of programmers' responsibility is very important. Today, programmers do not carry any serious responsibility. For example, a bug in the code controlling the Therac-25 radiation therapy machine was directly responsible for at least 5 patient deaths in the 1980s when it administered excessive quantities of X-rays. Another example: the software error of an MIM-104 Patriot surface-to-air missile system caused its system clock to drift by 1/3 of a second over a period of 100 hours, resulting in failure to locate and intercept an incoming missile. The Iraqi missile impacted in a military compound in Dhahran, Saudi Arabia, killing 28 Americans. Programmers are not responsible for such failures. Doctors who make such mistakes will lose their license. Programmers' working process is not regulated officially in any way. At the end of 2015, Robert Martin, aka Uncle Bob, wrote a blog post where he came out with the programmer's oath. To defend and preserve the honor of the profession of computer programmers, I promise that, to the best of my ability and judgment, I will not produce harmful code. The code that I produce will always be my best work. I will not knowingly allow code that is defective either in behavior or structure to accumulate. I will produce with each release a quick, sure, and repeatable proof that every element of the code works as it should. I will make frequent, small releases so that I do not impede the progress of others. I will fearlessly and relentlessly improve my creations at every opportunity. I will never degrade them. I will do all that I can to keep the productivity of myself and others as high as possible. I will do nothing that decreases that productivity. I will continuously ensure that others can cover for me and that I can cover for them. I will produce estimates that are honest both in magnitude and precision. I will not make promises without certainty. I will never stop learning and improving my craft. At least 3 of these points are strongly related to unit testing and test-driven design. The second, third, and fourth points are not possible to follow without practicing unit testing. Take your time to think about this oath seriously. Are you sure you want to be a programmer? The heart of any unit testing framework, from the developer's perspective, is its assertion model. Modern NUnit implements a fluent constraint-based model of assertions. What does it mean on practice? On practice, we use almost for all the assertions the that method. Here on the slide you see the signature of a generic that method. That accepts the actual result as the first parameter and the so-called constrained object in the second one. The most important thing here concerns the second parameter. Let's dig into the model of constraints. Constraints are the heart of assertions. I want to demonstrate this system from the practical point of view. I don't want you to cram into your mind all the internal types of the NUnit, so I'll try to simplify things a little bit. With no doubts, at the top level, we have three major logical constraints. Here they are: is, has, and does. These constraints are represented by the correspondingly named classes in the NUnit. The model of constraints is multi-layered. At the next level, we may have, but we are not obliged, other logical constraints. Here they are: all, not, some. This is not a full list, but I give you the most often used. Let's look at several examples of using these constraints. In this lecture, we will look at the examples on slides, and in the next lecture, I'll show you some examples in code, which you can download and play around with it on your machine. Take a look at the all constraint. The all constraint can be invoked both on is and has constraints. The first assertion here checks if all the items in the array contain the letter B. In this case, the constraint expression will be evaluated to true, since all the string literals contain the letter B. This constraint is comprised of two levels, is and all. The second assertion here checks if all the items in the array are greater than 0. In this case, the constraint expression will be evaluated to true, since all the values are greater than 0. This constraint is comprised of two levels, has and all. The not constraint can be invoked both on is and does constraints. Not is the constraint which allows you to build negative logical expressions. These examples are obvious, so I even don't see any reasons to explain the meaning of these code lines in details. The does constraint is most often used for writing assertions on strings. Here are three assert statements. The first one checks if the string ends with the exclamation mark. The second one checks if the string ends with the question mark. And the last one checks if the string contains a substring goodbye. Apparently, the first one returns false, the second true, and the last one false. The has constraint is mostly used with the some constraint. Here are two examples. The first assertion checks if the array contains any items starting with the BA substring. If there is at least one item satisfying this condition, the expression will return true. In this case, the second item starts with BA, so the expression will be evaluated to true, and the test will pass. The second assertion checks if there are any items in the array of doubles, which are equal to 1.0 plus minus 500th. The first item differs from 1 only on 100th, so the expression will be evaluated to true. Also, you can combine logical testing expressions by using compound constraints. Here's an example. Here I use the OR and AND compound constraints. By the way, the NOT constraint is also considered a compound constraint. Okay, so the overall meaning of this lecture is that with the modern NUnit, you can build assertions which resemble expression trees. In the next lecture, I'll skim through all the most common cases of assertions. Sometimes you want to group several tests explicitly. For example, you have several tests which run very slow, and you want to separate them into a group, logically. Look at how you can do this. For example, I'll pretend that these two methods run slowly. I'll mark them by a special attribute category. If you want to see this category in the list of tests, open the Test Explorer and group tests by traits. I need to rebuild the solution. Now you can see in the list the category of long-running tests. The category attribute is applicable at the class level as well. If we mark the whole testing class, all the tests will be in that category. All the tests from this class are now in this category. Sometimes you want to ignore a particular test. For example, if a test is temporarily broken. If you want to skip a test, mark it by the ignore attribute. Here's how you can do this. And the reason why you want to ignore this test. Let's rebuild. You can see an icon near the ignored test. The test runner didn't run this test. In the next lecture, you'll learn what is code coverage and how to calculate this metric. In the previous examples, when I showed you the features of NUnit, I intentionally relied on the simplest cases. The code under test wasn't dependent on any external systems, resources, or entities. But what if the code under test depends on, say, a processing center? If you need to test that such code returns something specific in case of a specific response from that processing center, what would you do? You can't just call a method which you want to test with specific input, since the processing center will not return what you want. Here on the screen you see a similar example. Let's say we want to test the calculate wage method, which implements a simple business logic. It calculates the final wage depending on the result returned from the getWorkingStatistics method, which is a part of public API of the DB Gateway class. Look at this method more carefully. It depends on two abstractions. The first one, which I have already said about, is the DB Gateway, and the second one is the logger. Obviously, the logger class is responsible for logging. Currently, it writes the information down to a specific file on the disk. What the problems we will face if we decide to check if the business logic is implemented correctly? E.g., if a customer is paid hourly, then calculate wage should multiply working hours on hour salary, otherwise it should return month's salary. I'm going to write a unit test in a straightforward way. And how am I supposed to name this method? What ID should I pass? 10? 20? 1000? The production code will try to retrieve data from a database using that ID.
And what should I expect as a result? I don't want even to continue to suffer trying to come up with a bright idea how to cheat the production code. It's impossible with the current implementation. This is not to tell that a real connection to a real database can experience a great number of issues. What would happen if you managed to write a test, but the production code can't establish a connection to a database? Right, your test will fail. Thus, your test will experience an uncertain behavior. It may pass in one run and fail in another. As you understand, this is a very bad thing. Okay, let's get back to the production code and analyze why is this happening, why we face such problems trying to write unit tests.
It's impossible to write unit tests for the code which interoperates with external dependencies directly during the process of unit tests running. All the tests you write for such code are integration tests, not unit tests. To write unit tests for code with external dependencies, you have to replace those dependencies with placeholders that you can control. It allows you to remove the factor of uncertain behavior of uncontrollable external dependencies. To turn such dependencies into controllable form, we can use different so-called test doubles, which fake the behavior of the dependencies. And here we reach the point when we need to introduce many testing terms and reach an agreement regarding their definitions.
Please, look at the diagram. On the very top, you see the term test double. Test double is a general term for referring to any special testing objects which replace the real dependencies to alter the behavior of an original object in some way. Below you can see one of the simplest forms of a test double called dummy. Dummy is a test double which returns values which are either null in case of returning a reference type or close to zero in the case of structures. At the same time, dummies just do nothing inside methods, which are not supposed to return anything. Below you can see the stub. What is a stub? A stub is a dummy which is set so that it returns predefined constant values from the methods called on the object which that stub replaces. We use stubs to drive the execution flow through specific pathways so that a unit test could test what it wants to. Dummy and stub are the test doubles whose intention is to check if the returning values and state changes are correct. Other test doubles belong to another type of testing, interaction testing. The next type of a test double is the spy. This is an interaction test double, and it concerns the so-called interaction testing. Interaction testing is testing how an object sends messages, or calls methods, to other objects. You use interaction testing when calling another object is the result of a specific unit of work. Let's give the definitions for remaining test doubles. Spy is a stub which saves some information about the calls made on the spy. It allows to verify in the test what argument values were passed in the methods, how many times any methods were called, in what order the methods were called, and any other information you may need to use in the assertion phase of a test. Mock is the most complex test double from this branch. Mock is a spy, but mock contains assertions inside itself, so a mock can fail the test. So, a mock saves some information, and if something is obviously wrong during the test, asserts in that mock will cause the test to fail. It means that mock knows what should happen in the case of one or another input values.
At first glance, the difference between mocks and stubs may seem small or non-existent. The distinction is subtle but important because many of the mock object frameworks that you'll deal with in the next chapters use these terms to describe different behaviors in the framework. The basic difference is that stubs can't fail tests, mocks can. Let me give the definitions of stubs and mocks once more. The difference is very important. The distinction between mocks and stubs is important because a lot of today's tools and frameworks, as well as articles, use these terms to describe different things. A stub is a substitute for a dependency in the system under test that allows the code to compile and the dependency to return data as specified by the test, but importantly cannot itself directly make a test fail. Don't get frustrated if you don't understand what does it mean right now. We will look at stubs and mocks in practice very soon.
In the other branch, we have a notion of a fake. Fake is the most complex test double. Yes, it's more complex than a mock. So, what a fake is in essence? Fake is a test double which simulates the behavior of a real dependency as close to reality as possible. You should avoid writing fakes. They are very hard to maintain in the long run. Each time a real dependency gets an update, you have to update the corresponding fake. Okay, let's write some unit tests with test doubles in the next lecture.
The problem of testing trivial code is related to test-driven design heavily, though it can be discussed without TDD involved. The question is, should we write tests for trivial properties with empty getters and setters or any equally trivial methods? And there are some different opinions even regarding this question. Robert Martin, aka Uncle Bob, initiated the most notable discussion, which was continued by Mark Seaman. In short, the meaning of the Uncle Bob's article regarding trivial code testing part of it can be distilled down to the following statements.
Don't write tests for getters and setters. Those getters and setters will be indirectly tested by the tests of the other methods, so there is no point in testing them directly. Don't write tests for one-line functions or functions that are obviously trivial. Again, they will be tested indirectly.
Uncle Bob states that TDD practices are not dogmas, and of course he is right, though his statements still require further investigation. Mark Seaman disagreed with Uncle Bob, saying that there are some problems related to Uncle Bob's statements.
They confuse cause and effect. Trivial code may not stay trivial, and it's horrible advice for beginners. The first question which comes to mind is how the hell properties and methods came into play without a failing test. TDD implies that we can't write code without having a failing test. Another concern is that very often practicing TDD, you don't know how much difficult the implementation will be. Another concern is that it might happen that at this particular moment a certain property is trivial, but can you be sure that it will not be changed after a week, becoming a calculated property with its own logic of calculation, which obviously should be tested? In my opinion, it's hard to give a universal advice which fits any possible cases. In my opinion, this problem belongs to one of many fundamental engineering problems which don't have easy answers. You must turn on your brain and deeply think about what you need and what you don't, what benefits do you see and what disadvantages you anticipate. Welcome to engineering! In the next lecture, you'll learn what test single concern rule means. It's very tedious to write the same declaration of a test method each time. We live in a world of powerful IDEs, so we can make our life easier. Download the special Visual Studio Code snippet file I attached to this lecture. Close Visual Studio if it is open, and then go to the following path and copy that file you downloaded to this folder. After that, launch Visual Studio and try to use the template. Here I'll quickly demonstrate how to use the template. I'll type in NUnit. Visual Studio discovers that it has such a code snippet. Then I'll press Tab twice, and Visual Studio inserts the snippet where you should only replace the placeholders with appropriate names. I type blah, press Tab, blah, Tab, blah. When you're done, you press Enter, and the cursor will automatically jump to the beginning of the test method's body. Very handy and saves a great amount of time.